Good afternoon, guys. Did you guys have a good weekend? Did anyone do something fun and crazy they want to share with the class? Pauline, what did you do this weekend?
I went backpacking on the Loyal South Trail in Wilton State Park. I saw that.
So it's crazy. We both went backpacking on the exact same trail this weekend. And I saw, there's a registry, like as you're backpacking for multiple days, people like write notes in it. And I saw UD Outdoor Club. I was like, oh, I wonder who's on that. After we both finished, we both ended up at a restaurant. It's like the only one in that area in Pennsylvania. And then she was there with a whole bunch of friends. She was leading the trip for the UD Outdoor Club. So if you ever want to go backpacking, talk to Pauline. She knows what's up. Join the outing club. Pretty random, pretty awesome.
Yeah, it's very funny. Someone was like, that's a YouTube professor at UD. I looked at one all the time.
All right, so tomorrow there are two things that may be of interest to you guys. One of them, is anyone interested in medicinal chemistry? Like how chemistry applies to drugs and treating of diseases. So at 4 o'clock tomorrow, the director of drug development at GlaxoSmithKline is going to be at UD giving a talk. Pretty awesome. 4 o'clock in Brown Lab 219. It's above my office in the front corner of Brown Lab. It faces over the green, looks at Memorial Hall. So if you want to go Brown Lab 219 at 4 p.m., I think it's a pretty good opportunity. This is the other one. So every year the Nobel Prize is given out to the people who make the biggest impact in the world, and that's in a number of different fields. Peace Prize, right? Went to Columbia's president this year, I think. The Nobel Prize in Literature, Bob Dylan. Nobel Prize in Chemistry, there's one in Physiology and Medicine, and then there's one in Physics. So what University of Delaware does is really cool, is that every year they say, we want to share with the community our expertise to help understand why these things were so monumental in the world. So they do a symposium every year. It's tomorrow night at 7 o'clock downstairs in the lobby here. They have experts from those disciplines around campus, and what they do is they share to everybody, this is the work that went into it, this is why it's impactful, and this is why you should care. So I highly recommend, if you have any free time on Wednesday night at 7 o'clock and you're here, go check it out. Everyone talks for usually, it's supposed to be like 15 or 20 minutes. Sometimes people like to hear themselves talk and they keep going. But I would really recommend checking it out if you're interested in doing research at any point in your career or to know what people have done and why it's so important. Anyone thinking about going? I think it would be worthwhile if you're around. All right. The other major thing is we have an exam on Friday night. Yeah, Friday night. I love it too. So we will have everything through class today, including workshop on Friday, will be fair game for the exam. The stuff you have in workshop Friday morning will help solidify some of the stuff about equilibrium, and some of the stuff in Thursday in class will do the same, so you'll be beyond where you need to be for the exam. So everything that was in class today is fair game for the exam.
Is stuff from exam 1 fair game for the exam?
Usually, so the final exam includes everything. As of right now, there's some parts of previous material that overlap.
Right.
But the stuff that doesn't overlap at all, we're focusing more on the stuff since exam 1. Any other questions? Do you guys want to do a scratch off for this exam?
Yes.
Does anyone not want to do a scratch off? Okay. So I'm going to plan to do a scratch off again. I've gotten very good feedback. We did it last night for 450 students. Sarah helped with that. She was proctoring. I think it went pretty well. It was super stressful trying to organize everyone because they'd never done it before. So we're trying to teach them. Anyway, whole nother story. It worked out well. So what we're going to do is we're going to just see if you guys got the last stuff on Arrhenius equation. We're going to talk about nuclear, and then we're going to get into equilibrium today. So I think this is on your worksheet from Thursday, sorry. You guys do not agree at all. Talk to the person next to you. Figure out if they're right or you're right.
child, I think, I don't know if it's directed towards the whole class, just said something about like an exam, how nice he's for
Last night, a whole bunch of students left for the CHEM107 exam. They left 10 minutes early, even though they just had to walk literally 100 feet from Kirkbride to Sharp Lab. Or, Smith.
She like just became our professor because our old professor left. So I thought she was maybe class Friday.
No. She was talking about yesterday. Did you have class Friday as well?
We don't have class Friday.
Yeah, so it was yesterday. About 100 of my students were in that class. All right, you guys are worse now than you were before you started talking, so you're terrible convincers. Would anyone like to talk through the thought process? No, that's not true. I'm going to pick on someone because I want to hear your thought process. Chelsea, what is your thought process on this? Can you guys bring it together? Hold on. Thomas. Thank you. Go ahead, Chelsea. Okay, so is there concentration anywhere on this graph? No. So the slope of this graph has nothing to do with the rate of change of the reaction. What is this graph showing? Cosme?
The ln of k.
So natural log of the rate constant is on the y-axis, and the x-axis is?
1 over t.
1 over temperature. So this all falls out of the Arrhenius equation. So somehow the Arrhenius equation lets us look at a graph like this and determine which of these reactions represents a reaction that has a catalyst added to it. So Justin, which of these did you choose and why?
I chose A because as temperature increases, the constant for the reaction it is like it's much larger compared to the blue line. I'm not sure.
So as temperature increases, which way do we go on the x-axis?
We go to the right.
1 over temperature. So if the denominator is bigger, then that's a smaller number. So that way is actually increasing temperature in this graph. So what are we supposed to get out of this graph? What is the main point we're trying to drive home with a graph of ln of k versus 1 over t? Brianna?
You got me.
What was the thing we talked about at the end of class? Taylor?
Is it saying that the catalyst, the reaction goes faster?
Okay, so we know with the catalyst the reaction goes faster, but what does this plot, using the natural log of the Arrhenius equation, what does this tell us? What information are we supposed to be able to pull out of this graph?
Isn't it because like before, like he was talking about lower temperatures, it will react with the catalyst, so that's why it might be the blue line.
So temperature, remember, doesn't affect the catalyst. Those are two independent variables. So where is the catalyst affecting this graph?
For this would be like your y-intercept form, where your formula is slope, so your slope would be activation energy over R.
Almost.
Negative activation energy over R.
So when you take a whole bunch of data points, you take one reaction, you change the temperature for it, and you look at, well, what is the rate constant at all those different temperatures? And then we take a whole second reaction with a catalyst now added to that first reaction, and we do the whole thing over again. And each time, we determine what the rate constant is. That's two different experiments at a whole bunch of different temperatures with the yellow, or the orange and the blue line. So if the slope of that line tells us that it's the negative activation energy over a gas constant, talk to your neighbor and try to decide which one of these two shows the same reaction with a catalyst added to it. Talk to your neighbor. Take 30 seconds. Click in your answer again. All right, go ahead and click in your final answer. Is everyone in? I don't even know what to do with this. Okay, let's take it stepwise. Thomas, when we add a catalyst, what happens to activation energy? Okay, so if activation energy gets lower as we have a catalyst, what happens to the slope of that line? Less steep. What does that negative sign tell us? The negative slope just said it goes from top left to bottom right. That's what that minus means. So if the magnitude of that activation energy is bigger, that means it's a steeper line. If it's a lower activation energy, it means it flattens out. It gets closer to a flat line. Woo. So the one with the larger slope is with or without a catalyst? So the one with the catalyst is our orange line. Is that? No, did I flip that? Sorry. Can't see what's under there. It's A. Okay? And I hope you know this from the y equals mx plus b version of this equation. The y-intercept is natural log of A, which is the... What's the term for that? Do you remember what A is in the radius equation? It's our frequency factor. We never really talked about A. That A is the largest total value that a rate constant can ever be. So let's take a look at that equation in the top left for a second. So the rate constant for any reaction, that tells us how fast the reaction can possibly go. If you have a small k for one reaction, a big K for another one, the one with the big K is going to go a lot faster. So if you think about as activation energy gets smaller and smaller and smaller, T gets bigger and bigger and bigger. That's how we make the reaction go as fast as possible, right? We lower the activation energy, we warm it up. So then what does that fraction become? What does this whole fraction become when we try to make the reaction go as fast as possible with the catalyst, lower activation energy, and higher temperature? It gets closer and closer to 0. What is e to the negative 0, or e to the 0? It doesn't matter. 1. So the biggest k can possibly be is A. And then the exponential component of it can only make it smaller. That number, e, is always going to be less than 1 based on whatever we put in the exponent. Does that make sense? No? We can talk about it afterwards if you want. Okay, so I'm just trying to give a little bit of insight on what those things are. There's the linear form of this equation. We just took the natural log of both sides. And what we plotted was y, our slope, this is our x value, plus b. So looking at that graphical version allows us to extrapolate and determine what the activation energy is. If you guys haven't already done so, there was another problem at the end of class on Thursday. The slides are up. You had it in your worksheet. You have to be able to do that for the exam on Friday. To look at a graph like this and determine what the activation energy is. That's exactly what that problem was, and I'm holding you guys to that. Questions? Okay. So our goals for the first part of class today when we're dealing with nuclear decay is you need to be able to predict when a nuclear decay might actually occur, looking at a particular reactant. You need to identify the components that are part of a nuclear reaction, and then looking at just an isotope with some information we'll talk about today, predict which ones are going to undergo radioactive or nuclear decay. So why do we care about nuclear reactions? What are some examples you guys have seen? Don?
How to make sure it's safe to get rid of waste from power plants.
Okay, so we use them to generate power because a lot of what's emitted from nuclear reactions is heat that we use to turn turbines, that we use to generate energy. So we have to dispose of those at some point, and we use them to generate the electricity. What other examples do we have of nuclear reactions? Val? Is that not you raising your hand?
No.
Chase? Dating like Tinder?
Yeah.
Okay.
No, objects found in the ground or just...
Okay, so how old something is. So this is a picture of a bone, right? If we want to know how old that bone is, if we go and we analyze carbon-14 versus carbon-12 ratio, we can tell how old it is because we know the rate constant for the decay of carbon-14. Other things, Taylor?
I was going to say medical uses of tracing things in the body.
Yep. We want to know, well, how long can we actually use this radio tracer? If we inject it into a person, is it something that lasts for 20 minutes? Or Or is it something that lasts for an hour and a half? Or does it last for 150 years, in which case we probably don't want to inject it in someone and have radioactive material there for that long amount of time. So there's a lot of different applications of nuclear decay. And up until now, I think most of our chemistry class, we basically said that an element is an element and it never changes. And that's a lie. There are certain elements that do undergo nuclear decay. So let's talk about that. Let's start off with this. You guys have already done a number of problems in your pre-class quiz for last Thursday, and you have some for your homework. So what remains unchanged in a nuclear process? So try to select your answer first, and then you can talk to the person next to you to see if they agree. All right, let's go ahead and close out. We are not sure. So maybe let's come back to this question. No, let's frame it. Let's frame the discussion based on this. So why is D the correct answer? The sum of all the mass numbers and charges of the reactants compared to products. Taylor?
So I think B because like carbon 14 goes to nitrogen, so it's changing the number of protons. So I said A wouldn't be right, and then I was unsure. Well, C wouldn't be right because you could change the number of electrons. So I didn't know about B, but because energy can't be created or stored, that's 50.
Okay, great. So I love it. So your definition goes back to the simplest philosophy that you can't create or destroy mass. And so what we're going to be talking about today is that under nuclear reactions, a proton can become a neutron can become a proton, but in order for that to happen, the charges also have to be balanced. So that means an electron can be absorbed or an electron can be released. The sum of all the charges has to be the same on both the left and the right side. The sum of all the masses has to be the same on the left and the right side. What kind of a reaction? Why is B not a nuclear reaction? Oh, sorry, C. Why is C not a nuclear reaction? Brianna?
Electrons aren't in the nucleus.
Fantastic. Okay, so definition of a nucleus is the nucleus, which is where the protons and neutrons are. And electrons can be removed or added. That's not a nuclear reaction. That's ionization or adding electrons. So I think almost no one chose that. Is that right? Dang it.
I totally chose it.
You what?
I totally chose it.
You own it. You're like, yeah, I did it. Okay. So let's not do that in the future, Brian. You good?
Yeah.
So when does nuclear decay occur? Select all, or type in all of the numbers that apply. So if you think it's 1 and 3, type in 13. And these are questions 2 and 3, I believe, on your worksheet. Another 10 or 15 seconds. Talk to your neighbors, see if you guys agree. No? No, that was a little bit on purpose. All right, let's see what everyone says. We only have 32 clicks. So 2 and 3 are by far the most popular. What is number 1? Why is that not a good option?
Because it's an ion.
Because it's an ion, and ions might be stable, they might not be stable. If they're not stable, they're going to gain an extra electron, or they're going to give up an electron. So that's not a nuclear reaction. All right, so then 2. When the ratio of protons to neutrons is unstable. That's kind of our definition for when a nuclear reaction will occur. So there's a PhET simulation. If you guys want to practice this, if you Google PhET, P-H-E-T, and atom builder. You guys might have used it at the beginning of CHEM108. You can literally put in a certain number of neutrons and protons into a nucleus, and either starts to vibrate, it says it's unstable, or it says it's not. On your guys' worksheet, you have something called the belt of stability. And that belt of stability shows us what a stable ratio of protons to neutrons is. If you notice, the y-axis is the number of neutrons, x-axis is number of protons, and there's a certain ratio that seems to be very stable. The other part is there any stable isotope past 84 on the x-axis? There is not. So why is number 4? Why do some people choose number 4? Because what? Okay, so maybe something to do with isotope. Chase? Okay, so if we're talking about proton-neutron ratio, there are certain ones that are considered stable. And so what I was hoping is that someone would say, well, you can't say everything all the time, and that is saying that basically there's always going to be some form of stability. It's just a matter of time. But that's not true. There are certain isotopes that are actually stable that will stick around until the end of time. So I agree with you guys that 2 and 3. So if anything has an unstable ratio of protons to neutrons, or if it has more than 84 protons in the nucleus with any other number of neutrons, we don't have any stable examples of those existing. So let's look at this belt of stability. So I want you guys to look at the belt of stability that you guys have written out. What is the stable ratio between protons and neutrons? Talk in your group. Try to decide what is the stable ratio that you see. So after 20, it's stable? Look up here, you mean?
I think it's on the dotted line. It starts after the 20.
So the 1-to-1 ratio is that dotted line. The stable ones are the black dots. So which ones is the dotted green line the stable ones, or the black dots the stable ones? Black dots are stable. So if we have a low number of protons, if we have 20 or less protons in the nucleus, what is the stable ratio, Michelle? If we have 20 or less as our atomic number, what's the stable ratio?
Like 1 to 1.
So down here it's about 1-to-1. But then what does it trend towards as we have more and more protons in the nucleus? Katie?
3 to 4.
What's that?
4 to 3.
So it's about 4/3 or something like that. Is that what you're getting at?
Yeah.
That it's up above. It's actually a higher number of neutrons compared to the number of protons. It kind of makes a little bit of sense if you think about if you have 84 protons, positively charged particles, all crammed into the nucleus, that's a huge charge density of positive charges. So Einstein's theory of E equals mc squared, if you were to add up the masses of all of the nucleons in a nucleus, the individual masses, and then you say, well, how much does that atom weigh? It's not the same. And the difference between how much they should weigh and how much they do weigh, it's called the mass difference. The mass difference is the amount of energy required to hold those things together. So literally, the energy that we get out of nuclear reaction is by pulling those apart, we release that binding energy that holds that nucleus together. And this is some Einstein stuff that just blows my mind. Taylor?
I understand what you're saying, but I just don't understand. Like, is the nucleus one size and the
So the nucleus is,
Like, why doesn't it just keep getting bigger? Like, why can't?
because the stability, it won't hold together. So there's not enough binding energy to keep that many positively charged protons together, no matter how many neutrons there are. So it's not the same size. So you think about a nucleus, right? There's particles that are physical and they take up space. And the more of those we pack together, the more positive particles there are. And once we get above a certain number, no matter how many neutrons there are to help kind of stabilize it, it's no longer stable and it falls apart. So we can find things that are unstable. And if you look at this, the gray dots are nuclei that are found that have either been made or have been found. What's the most common form of radioactive material used in our nuclear reactors? Uranium. What's the atomic number of uranium? Anyone have their periodic table handy? Uranium. I think it's just U, right? 92. So is this stable?
No.
Are there any stable isotopes of uranium?
No.
None at all, because it has more than 84 protons. But we can enrich it, we can find it. So something that's left over from billions of years ago, if we isolate and enrich uranium by itself, then we can harness the energy when that nucleus falls apart and undergoes nuclear decay. It does so predictably, but we do it under a very controlled environment to make sure that it doesn't get out of hand. So what I want you guys to be able to do with this image is if I were to give you any isotope of any element, you would have to say whether that is stable or unstable. So what if I told you guys that we had something that was, I'm going to give you a letter, I'm going to say if it's X, this element, is this element stable or not? Talk to your group, try to decide. What do you think? Okay, so that's one of the two categories. What's the second one?
Well, the atomic number.
The ratio of protons and neutrons.
So how many protons and neutrons does this have?
It's not.
So find it. It's a data point.
2 is 72.
Find it.
72.
72 is what? So how do we find the number of protons and neutrons? All right, so raise your hand if you guys think this is stable. Is it stable? Raise your hand. If it's unstable, raise your hand. If you have no idea, raise your hand. So how do we figure out this is stable or not? You want to use this to help describe?
Yeah, sure. Okay. Oh, okay. Can you not see where you had written the other stuff before?
Other stuff's in the top right corner.
Oh, I see. Well, you have 78, right? And that's your atomic mass. And you have 36 protons. So to get to 78, you would have 42 neutrons. And
Does everyone follow so far?
okay, so you have 78 is the atomic mass, correct?
Which
And
is
the addition of the neutrons and protons and electrons, but they're not really.
no, it's not. Oh, so we don't consider.
Yeah, you don't
electrons.
consider the electrons for
So
this
it's the
number.
sum of all the protons and neutrons. That number is that top left number. So that's the isotope.
And
the mass number.
on the bottom, you had 36, which is how many protons the element has. So you subtract 36 from 78 to see how many neutrons there are, and that was your 42 value right here. And then on that, you look on the graph, and then you just find it on the plot, and then you find 30, 36, which should probably be around here, and then 42, which is here, so it'd be
Big X
around.
across where you found.
Okay, it's selected.
Big X.
Yeah, it just selected. Kind of around there.
Okay. They're gonna follow what Chase did.
Wow, my X looked a lot bigger on this.
It does look a lot bigger on your screen, so I'll make it a star.
Thank you.
Okay. That's how I need you guys to be able to use this graph. To say, if we were to find this isotope in nature, is it one of the stable points, or is it not? So let's try another one. What if instead we had, let's do Y, Let's do, is this stable? All right, so mommy, what do you think? Is this stable or not?
I would say it's stable because you have 47 neutrons and 36
Okay. Do you want to highlight where that would be on this graph? Maybe draw a line up from 36 protons to where it would be. Okay, so that still might fall in the belt of stability. Everybody agree? And we really need a zoomed in version in order to see it. So what if instead we had an isotope that was out where that blue X is? Let me do another color. Let's do purple. Where that purple X is, would that be stable? How would that isotope change in order to be more stable? Alex? It would decay in what way? What would have to change about it? What would have to go down? So if its mass goes down, there's a nuclear decay process called alpha decay. When alpha decay happens, it ejects an alpha particle, which is this. What is that? Something that has 2 protons and a mass number of 4. What is that? It's a helium nucleus. It's not helium, right? It doesn't have 2 electrons. That's an He2+. So if it lost that, that means it loses 2 protons, 2 neutrons. Does it become stable after that? So an alpha decay wouldn't help this become more stable. So that doesn't happen. So what would have to happen with that element is it would have to convert a proton to a neutron or a neutron to a proton, which would help it become more stable. So if it converted a neutron, it would lose a neutron, it would gain a proton, it would go down to the right. So let's talk about all these different ones. I was just going to kind of ground us in this figure here, but we're going to talk about specific ones. So let's talk about electron capture. I want you to summarize what's happening in electron capture. Be really specific. Pay very close attention to the notation. You see that. Because I imagine this could be left field. You know, like ground it and come back to it. All right, make sure you talk to the person next to you. Not everyone's clicked in. I imagine that means you're not quite sure. What changes do you notice? How do you know it's happening? Can I get you guys to maybe merge and join these guys for today? It'd be useful. Thanks a lot. Tatiana, Salma, do you guys mind opening up a little bit and having Thomas and Dan join you guys? All right, so let's go ahead and submit your answer. McKenna, you want to talk us through your thought process here?
Oh, no.
So if the protons go from 6 to 5, so I said G, so you're
How do you know that that proton made a neutron? Okay, so we know that the number of protons went down 1. So we started with a proton, which the generic terminology is this. What is the number on the top left, by the way? Let's just make sure everyone's on the same page. The number on the top left is? That's the mass number. That's how much weight there is in that thing. The bottom number is? Not just proton. It can be minus or plus 1. So what is it? So if we're talking about an element, yes, but in our shorthand notation, the second thing, the E with a -1, the bottom left, what does that mean? It's an electron, so that bottom left number tells us about charge. So it's a carbon 11 plus an electron. This is an electron, which is also written as a beta particle. This is the same thing as what we see on the left side there. So how do we know that we gained a proton going from left to right, McKenna? So on the left side, how many neutrons do we have? Left, we have 5 neutrons, and on the right, have 6. So by doing the deductive reasoning, seeing what we lose, what we gain, we should be able to back out that this must be that we had a proton combining with an electron, which I'm going to use beta particle here, and that generates, a neutron. This is the condensed or shorthand notation that just looks at what changed. Don?
I just want to make sure I'm remembering this correctly from Chem 1. Is that process, that proton to neutron, is that a neutrino or is that something else?
No, neutrino is something else. Neutrinos are parts of like what make up protons, right, and neutrons. So I don't actually know. That's particle physics that's even smaller, though. Does anyone know what a neutrino is and want to explain what it is?
I thought it was this, because I had read about this and it said that electron captures an electron, proton make a neutron, and then it's called a neutral, whatever she said.
Neutrino? Okay, so I'm not 100% sure. I need to look into it. And maybe you can... So it might be. So I thought a neutrino was like quark level stuff, but I could be wrong. So maybe you can look it up. I'll look it up and post something on Canvas Discussions to clarify that. Thanks. Taylor?
I have a question. So you can't go from like an electron and a proton to make a neutron because it's like a negative and a positive. It cancels out. But you can't go like proton, neutron to electron, right? It's like
So what has to be conserved from left to right?
the charge,
Charge and?
the mass.
So we could never have a proton and a neutron combining to get something with no mass. We basically say electrons have no mass because relative to protons and neutrons it's 0. So what I want you guys to notice about the equation that I wrote at the bottom there is that the sum of the masses is what? On the left side. Sum of the masses, 1 and 0, so it's 1. On the right side it's 1. So I'll circle those in red. So the masses are 0 and 1. That is the same on the left and the right side. Sum of the charges, minus 1 and 1, which is 0. So that first question about what's conserved in any nuclear reaction, we can't just get rid of a proton. The proton may be converted to a neutron by absorbing an electron, or we might kick out a whole other particle, which is an alpha particle, and that contains things. But we still account for it, it's just now in 2 separate locations.
Wait, are beta decay and electron capture the same thing?
So let's do that. Let's look at it. So we'll come back to it. Why do I say that this happens with neutron-poor nuclei? What is neutron-poor nuclei even referring to? Michelle? Okay, so it's not just more protons than neutrons. We go back to here. It's compared to what's stable. It has a higher ratio of protons and neutrons, so it's neutron poor. So which direction do we go if we convert a proton to a neutron? Does it go up and to the left or down and to the right? So we lost a proton, we go in this direction. We gained a neutron, we go in that direction. So overall, that process is moving us up to the left, which can increase stability of nuclei. What were you saying? You went after that, or?
No, just not mentioning I can create arrows.
My arrows are terrible? Yeah. So if it starts as neutron poor, it means it has a lower ratio of protons to neutrons, that there's less neutrons and it needs to be stable. So by converting a proton to a neutron, it moves in the up left direction and gets closer to the belt of stability. Let's take a look at another example. Yeah, Taylor?
So, the electron has to go inside the nucleus.
So the proton absorbs the electron and becomes a neutron. So yes, the nucleus absorbs an electron in order to become a proton. So let's talk about beta decay. What's that?
It's just like, nothing, it was just like the clicker thing from like 33 to 37 real fast in the last question.
Interesting.
Like you said, it was
I don't know why. All right, so then what is beta decay? Let's look at this as an example. This is what we use for carbon dating. You were asking about beta decay, right? No, I was just making sure that that was the decay process you were asking about. So Val, I want you to describe how they relate to each other. To the whole class. You're getting it? What are you guys thinking? Seems like a logical way to talk through it. All right, is everyone clicked in? Katie, do you want to explain your thought process? Can we get everyone together? Let's do one of these guys.
From the left to the right side, on the bottom number, it gains positive charge and then electrons pulled out. So I said A.
Okay, so we have 6 protons to start with. We end up with 7 protons. What happened to the total number of particles that contain mass? Stays the same. So if that stays the same, but we gained a proton, it means a neutron must have been removed from the nucleus. So then what's the generic equation going to be for this reaction, for a beta decay? Shane?
The neutron, so 1, 0, 1 on top, 0, neutron, becomes 1, 1 proton, 0 minus 1.
So a proton is, neutron is decaying, becoming a proton and an electron. So Val, how does this relate to electron capture? It's exactly the reverse reaction. So would this be more likely? Would this be likely to happen to a neutron-poor nucleus as well? It would be a neutron-rich nucleus because it would move in the opposite direction according to the belt of stability. So I agree that this would be a neutron decays to form a proton and an electron. There's their generic equation. So this is what we use for radiocarbon dating. Is that up in the atmosphere, we have neutrons from the sun that bombard our atmosphere. They collide with nitrogen molecules, N2. And every once in a while when those collide, the opposite reaction occurs. This reaction actually is a physical process in which the nitrogen has components kicked out of it. I don't want to focus on that reaction so much. But the idea is that in the atmosphere, we always have a ratio of carbon-14. A certain fraction of the atmosphere is carbon-14. and then most of it is carbon-12. The plants, when they grow, they photosynthesize, they take in carbon in the form of carbon dioxide. So they basically freeze whatever that ratio is in the atmosphere. They bring in that exact ratio. But because carbon-14 decays over time, every 5,700 years, that carbon-14 decays by half. By beta emission, that means that if we look at a sample over time, we can find less and less and less radioactive carbon in it. So how far can we go back with radiocarbon dating? How old of material can we actually determine the age? Yeah, I'd say about 50,000 is the number we typically throw around, so about 10 half-lives. And then what types of material can we not use radiocarbon dating for?
Something that's not made of carbon.
Has to have carbon, right? If it doesn't have carbon, we can't use radiocarbon dating. So let's look at the last type of decay that we're going to be focusing on this class. So talk to your neighbor, what is happening in this type of nuclear decay? This is uranium decaying to thorium. What happens? And does this still obey our rules for what has to happen in a nuclear reaction? So what's happening here in alpha decay? 2 protons. Anything else? Yep. So what do you mean forming?
Because it's like not there before, but it comes at the end.
It's not being made, right? Where's that helium nucleus coming from?
Like it's taking out 2 protons.
Yeah, that's an example, but it's decaying.
Is it coming from the
So that uranium splits apart. It's actually breaking apart the nucleus, and a chunk of 4 nucleons come out, 2 protons and 2 neutrons. You guys want to explain that? Dana, it's all you. Dana, would you please explain to us what happens during alpha decay?
the uranium splitting up, and a helium nucleus is like part of it that got split up, and then 2 protons. What I even said.
Brooke, you want to add to that? You want to help clarify?
It's like, I don't know, I feel like it's hard to explain, like, it seems like it's splitting up into 2 atoms, and then one of them, like, 2 protons are then lost, like, so like 2 neutrons. Or, like,
Yeah, so it really is about if you have a nucleus that is so big and has so many nucleons in it, that if that splits apart, it increases the stability of that nucleus. So what it's doing is it's splitting one nucleus into 2. That second nucleus is an alpha particle. That's really the only way that we see nuclei splitting apart and actually like fracturing the components of the nucleus. Chase?
Does that alpha particle become like helium?
The alpha particle is like helium. What does it need in order to become? If it steals 2 electrons, it is helium. Absolutely. So that fracture, that fission, or that fission, of 4 nucleons, 2 protons and 2 neutrons, splits off, and we call that alpha decay. So I think you guys are already okay with this being a helium nucleus. And so a lot of the stuff that we talk about in first semester chemistry, we talk about the experiments that Rutherford, Geiger, and J.J. Thomson did in order to describe what the nucleus was. They originally thought that an atom, their model was the plum pudding model. Before they knew what a nucleus was, they said, well, I know that electrons exist. We can pull an electron off of any element. We can see them. They're particles. So then they said, well, if I know those are particles and I know it's neutral overall, then my proposal is that the whole atom has a diffuse positiveness to it. So they call that the plum pudding model. That the plum was the little dots, and the pudding was the big thing that was diffuse. And they knew that certain elements ejected radioactivity, and they ejected alpha particles. They didn't know what the alpha particles were, but but they use these in their studies. So if this model were correct, this plum pudding model, what would happen to alpha particles that they would fire at these atoms if the plum pudding model was correct? And maybe I should include a little bit more background since I talk about a metal sheet. Rutherford's experiment was he created an incredibly thin foil of gold metal, and then he fired alpha particles at that gold foil. And it was so thin, it was just a couple of atoms thick. So if this model held true, then they have kind of drawn up here what they would predict to happen to those positively charged alpha particles. So maybe actually this question isn't quite about if it's... So let's just actually answer the question itself. What do you predict actually happened instead of... So read the question carefully, answer the question the way it's worded. When they did this experiment, what would you predict happened versus what would they predict would happen?
Are you saying what do we think happened, or what does it look like that diagram is saying?
This is their initial hypothesis. What do you think actually happened? So Brian, what were you describing? Okay, so if the alpha particles are positively charged, and instead of being a diffuse positive, if there's a dense positive core, then the alpha particles bounce off of that. Is that what you're saying? Yeah. So does that mean that all of the particles fired at it are going to bounce off? What do we know about the relative size of the nucleus compared to the atom?
Really small.
Stupid small, right? It's ridiculously small. So this is more of the image. And so what Rutherford found was that when he was firing these alpha particles at this thin foil of metal, that most of the particles went completely through and didn't interact at all. And there wasn't this slight deflection as he thought with the plum pudding model. So the nuclear model was that most of them passed straight through and a small fraction of them were deflected back. So this is what the experiment looked like. He had an alpha particle emitter. He had some radioactive material that emitted alpha particles. He fired at the gold foil. And unlike his prediction, which was that you'd have a scattering of the particles on the far side, we actually ended up with some back towards the detector. This is how they actually determined that a nucleus existed, and it wasn't a diffuse positive core. So this is kind of what you can do with a little animation, is say that there was some deflection, but that every once in a while you'd have an alpha particle that would bounce off the nucleus of gold, and it would bounce back in the direction it came from. There's other types of radioactivity as well that we haven't really gotten into, and we're not going to spend too much time on. And I'm actually going to skip through all these because I want to get into the second part of today. So before we go too far, what questions do you guys have on nuclear decay? Can you identify an unstable nucleus if I give you the belt of stability? I will give you the belt of stability on the exam. Can you predict what type of decay will happen in order for an element to get closer to the belt of stability?
Was it 3 types of decay we just talked about?
There were 3 types of decay we just talked about. When is alpha decay going to happen? When there's a lot, Pauline? When there's a really big nucleus, specifically, how big? If we have more than 84 protons in a nucleus, then the only way to decrease the number of particles in the nucleus is alpha decay. Any other questions?
Are there any more practice problems for these?
Smart work. Yes. Always the right answer. Smart work. Yes, I'll put up some questions on smart work. So it's not going to be a huge focus of our exam. Basically, we know that we can predict with these types of decay how long until a certain amount is there. We can find our rate constants. All of this ties back in because what type of decay do radioactive material undergo? Maybe that was poorly worded. What rate order do all nuclear decay processes? They're all first order. So we should be able to make a whole bunch of predictions, and I wanted to show a little bit of what that involved, and get out of the mindset that every single nucleus is exactly what it is and won't change.
Can those gases go through decay?
Anything can go through decay if it has an unstable ratio of protons and neutrons. So if you were to go back to the belt of stability, you could find the number of protons that a noble gas has and see what unstable versions of that. You'd have to go to the slides where it has the gray around it, which ones commonly exist in nature. Don?
We said alpha is when it's 84 protons. Is beta when it's less than uranium is once it gets to 84, will it decay in a different way?
It can, or it might be stable. So uranium becomes thorium, thorium becomes polonium is the next jump down, and then polonium becomes lead. That's the typical decay process for nuclear reactors. It depends on which one of those you get to, whether they're stable or not. They might undergo electron capture, they may undergo beta decay, they might undergo different processes in order to become more stable. But really, if you say that in order to stabilize, they need to decrease the number of nucleons, they're out to the right of that, then alpha decay is going to be the first process that actually achieves greater stability. And then we need to say, well, where does it end up and where might it go from there? All right, so let's get into what you guys have already spent a decent amount of time with. See, big picture, what you guys are comfortable with. Do another 10 or 15 seconds. All right, closing out. So almost everybody said false. Kirk, do you want to give us your thoughts on why this statement might be misleading and hence false?
Concentrations aren't the same. They aren't necessarily the same.
Okay, so what is the same? Maybe we'll get a little bit into that in a second here. One of the biggest misconceptions when students start equilibrium, if they haven't done the POGL activities that you've done, is they say equal concentrations. That's equilibrium, right? And that is totally false. Almost all the time, you will never have a concentration of your reactants equal to the concentration of your products at equilibrium. So what about this statement then? A couple more seconds. Miata, I want you to describe this one. All right. Miata, you want to share your thoughts? So at equilibrium, it's not that the reaction stops. It's that the products are becoming reactants at the same rate as reactants are becoming products. So one kind of visual I try to use for this is to say during the day here between maybe 8 a.m. and 4 p.m., what would you say about, on average, the number of students in the building? Is it fairly constant? The number of students in the ice lab from 8 a.m. to maybe 3 or 4 p.m.? It's about the same, right? Does that mean that no one's coming in or going out? So there's a constant flux in and out of the building. The total number of them isn't changing. The concentration inside versus outside isn't necessarily changing. So what do you guys think about this last one? Closing out. All right. So this is really our basic definition of equilibrium. When a reaction gets to equilibrium, that means that the rate at which things are going in and out of the building, if you will, the rate the reactants are becoming products are becoming reactants, is the same. And I really hope that you guys can think back to workshop when you had that table of data. The number of A becoming B, the number of B becoming A in the same time frame, it didn't go to 0. It never goes to 0. It just goes to the same amount in each direction at any one period of time. So my objectives for the second part of class, which we'll be digging into, is based on the rate of forward and reverse reaction to be able to define equilibrium, like we just did. Talk about the difference between no net change and a reaction stopping. And then talking about based on the rate constants, we're going to have a couple of different Ks we're going to start talking about. It's going to be really, really important to not just say K anymore, like I did in the beginning of class. Our K is either going to be not OK. OK is fine, not K. K is either going to be the rate constant, and K is going to be the equilibrium constant, which is capital, which is lowercase. Brianna?
Equilibrium constant capitalized?
Our equilibrium constant we're going to start talking about is a capital K.
Isn't it K sub C?
It can be K sub C, K sub EQ, a whole bunch of different things. If you see a capital K, that is an equilibrium constant. Lowercase, that is our rate constant.
Are we never using temperature in this? Because capital K is only Kelvin.
So if it's a unit beside a temperature, then it's Kelvin. But if it's a constant
If it's in a
by
degree,
itself,
it's that.
you can. It should be very easy to tell whether it's Kelvin or not. All right. So by the middle of class on Thursday, you guys should be able to write out an equilibrium constant. We might be able to do a little bit of it today as well. All right. So let's ask the big question: are we at equilibrium? Alex, are you at equilibrium? Do you have any chemical reactions in your body? Are all of your chemical reactions at equilibrium? What did you say? Alex, what do you think?
Am I equilibrium right now? No.
No. When are we at equilibrium? Sarah? Okay, so if we're asleep, are we at equilibrium? Jose, what do you think?
I think we're never equilibrium.
We're never at equilibrium.
Equilibrium for what?
We are at what kind of an equilibrium? Homeostasis, which means that we have a set value we need to have in order to survive. Is that the most stable form of all reactants and products in all reactions? That means, at equilibrium means once you take off any external influences, that reaction goes to the most stable place possible. Is that true of where my hands are right now? That's physically, that's more stable, right? So think about everything going on in our bodies. If those were to come to a resting point at the most stable chemical structures, what would that look like? It wouldn't even be a dead guy. That's still not at equilibrium, right? That would be after we're decomposed, completely gone. So we are at all costs trying to avoid equilibrium. These are all the processes that are having energy put in to keep them from being at equilibrium. Our bodies are very much not at equilibrium. There's a dynamic equilibrium we try to maintain. We're driving the reaction to one thing in order to make our chemical reactions go. We eat food to give us energy, to push those reactions away from where they would want to be at rest. So let's talk about a physical equilibrium. So equilibrium can either be physical, which means change of states, or it can be a chemical, which means chemical bonds being changed into the most stable relationship between reactants and products. So we have a normal physical equilibrium that we are hopefully all incredibly comfortable with. H2O, solid to liquid. Go ahead and click in your thoughts on this question. This is also on your worksheet. Oh, those are forward and reverse. Okay, I'll mention that. All right. Has everyone clicked in? So if our polar ice caps are not melting, then we can say that the rate of melting is equal to the rate of freezing. That means that our ice caps don't get bigger, they don't get smaller. But we know that that's not true. We know that over a span of a century, our polar ice caps have shrunk drastically. So what can be said about the forward rate versus the reverse rate for this phase change? Forward. Forward and reverse. So that's what's rate of melting, rate F, forward. So this equation here. So just to clarify, what does the F stand for in the rate F? Forward reaction, and that is incredibly specific to the way I wrote the reaction on the top left. If you guys write the reverse reaction, if you write going from liquid to solid, then that would change your definition of forward and reverse. So be really careful. When we have a direction of a reaction, it has to be talking about with that on the left and the other on the right. So if we have our polar ice caps melting, what do we say about the relative rates? It looks like everyone's saying that the rate of the forward reaction is increasing. Why is it increasing? Why is the rate of this forward reaction increasing? Kristen? Because global warming, temperature is rising because?
Well, I was gonna say I thought you were gonna actually talk about the equation. I was just gonna say because it's going from solid to liquid faster than it's going from liquid to solid.
Okay, I like that. So getting back to the equation, talking about the physical equilibrium, that we're actually driving it more to the right. So that means the forward rate constant has to be increasing, and the reverse rate constant is decreasing. Megan, you can answer why?
Well, I was gonna say pretty much the same thing, that it was melting at a faster rate.
Great. So if that equilibrium is now perturbed and we don't have a constant equilibrium, over time, right? Every summer it melts, every winter it freezes. But if those changes end up shifting in the direction of more and more ice melting, then that's a big concern of ours. So let's talk about chemical equilibrium then. So chemical equilibrium is achieved when a chemical reaction gets to the most stable mixture of reactants and products. So that is when the rate of the forward reaction is equal to the rate of the reverse reaction. You guys are pretty comfortable with that definition, I think. That means that the concentration or the net number of reactants and products doesn't change anymore. So what part of this graph is the kinetic phase? Which part of it is the equilibrium phase? So Sarah, you want to share your thoughts? What's the kinetic phase? What's the equilibrium phase?
Everything to the right of 7 seconds is equilibrium.
Why?
Constant, like they're all
So that means that on the left side, we have the rates of production and consumption are changing all the time. But once we get to 7 seconds, this reaction seems to have no net change in concentration. So that right side is our equilibrium phase. The left side is our kinetic phase. And what we're going to be talking about and using these graphs that are those blocks on your page is that anything that is at equilibrium, we cannot use that to drive anything else forward. There is no free energy available. Everything on the left side, we're talking about that we can use those reactions to drive other reactions forward. This is what we use to tether reactions that our body uses to generate energy, to generate momentum in order to do other things. You can think about it as a boulder sitting on top of the hill. Once the boulder's at the bottom of the hill and it's the most stable place, you have no more energy to do anything. If we push it to either side of a valley, that's going to give us momentum in order to get something done. Might be the wrong direction for what we want, or it might be the right direction for what we want. So here's that analogy, that if we have a valley and we have a rock that's sitting on top, that this, if we have something down here and we want energy that helps push us to the right, the boulder is in a really good place right now. That when it goes to equilibrium, it's going to give us a push in the direction that we want. If it's on the other side, not so ideal. But it still has energy that can be used for something, maybe just not what we want it to be used for. And so what we're going to start drawing is these Gibbs free energy diagrams that represent a chemical reaction. And let me center you guys a little bit. So on the left side of any of these reactions, the x-axis is the course of the reaction. So what's on the far left side of the reaction? What's over here? This is 100% reactants. When we are there, so this line would keep going up, and this is not the same. On Thursday, what we're going to do is we're going to contrast an activation energy diagram with a Gibbs free energy diagram. They're two completely different graphs. They have some similarities, though. So when we're at 100% products, is this reaction stable? Is it at equilibrium? Why not, Sabrina? If we're up here, are we at the most stable place? Where's the most stable place? Down here. So this reaction is going to proceed downhill. It's going to move towards the right. What's on the far right side of this graph? Over here, we would say this is 100% products. Is this reaction 100% products at the most stable mixture? What is it, Don? What would your guess be? What's the ratio of reactants to products when this is most stable? Give a relative value. Okay, so if it was 50-50, it would be close, but it's not quite. 60-40, what's 60 and what's 40?
The products are 60 and
So 60 products,
40 reactants.
40 reactants. I'd agree with that. If it was a 50-50 mixture, the equilibrium would lie right in the middle.
So is it more stable to be at equilibrium with products?
So if we're at products, we're going to be over where this line would keep going to 100% products. We'd be up here. Is that more stable? Or is...
I just thought that because I thought reactions go to
Yep.
the products would be the most stable. So why doesn't it just stop at equilibrium?
So you've been lied to your whole life to say that products of a reaction are more stable than the reactants. This is actually how it exists. When you run any chemical reaction, or any chemical reaction happens, I'd say about 1 billion to 1 chance you will actually end up at products, all products. So as a synthetic chemist, I spent a lot of my life trying to develop and design reactions that would go as far to completion as possible, and it almost never happens. So chemical reactions, while we draw them from A to B, we never get all B. That we find some point that's more stable, we try to generate reactions that have a value further to the right, but that does not happen very often. So our equilibrium constant, the last thing I think we have time for in this class. Equilibrium constant, big K. What is that? Justin?
Isn't the concentration of product
raised to the stoichiometric coefficient. So if this is just A to B, what is equilibrium constant for this reaction on the right?
B to the 1 divided by A.
Okay, but let's give a number to it. Based on, you said 60-40 mixture. Not quite. If it's 1, then that would be 50-50.
So
3 over 2, equilibrium constant for this reaction, big K, is 1.5. So we're going to start dealing a lot with that equilibrium constant. And one last thing, there's two ways to look at equilibrium constant. One is when it's at equilibrium, that's the red ball. But at the green ball, are we at equilibrium? Could we describe the same ratio of products to reactants at the green or the blue spheres? So if we do, we call that Q. It's the ratio of products over reactants. One more comment from Ms. Terrell?
I just want you guys to bring your notes tomorrow to the studio. We're going to be addressing concepts of equilibrium a lot more. So definitely bring them to make sure you have something to fall back on when needed.
And then I would, if you have time, I would highly recommend going through question 17 on your worksheet.
Is there a unit for K? Is
Um,
there a unit